equals x minus the mean divided by the standard deviation. So z times standard deviation equals x minus the mean, and z times the standard deviation plus the mean equals x. So let's if you have math anxiety, that's sure to give you a conniption. So let's look at the example. For mean equals 200, standard deviation equals 50, and z equals plus 3, what's the value of x? Without using the formula, you can do it in your head to get x equals 350. Let's do it with the formula. X equals z times standard deviation plus the mean. So that's 3 times 50 plus 200 equals 150 plus 200 equals 350. Okay, that wasn't too hard, was it? So here's the summary. What's the purpose of a z-score? Raviter and Wallnow says that each z-score tells the exact location of the original x value within the distribution. Okay, so it's just telling me on the x-axis of the curve, let me draw it. On the x-axis of the curve, this is the x-axis, okay, x. Where is the score? Where's that x score? Is it here? Is it here? Is it here? So that's what they do. Each z-score tells the exact location of the original x value within the distribution. What's the distribution? Everything in the curve. The z-scores will form a standardized distribution that can be directly compared to other distributions that have also been transformed into z-scores. So if we have apples and we have oranges, we're transforming them both into z-scores. So we can now really compare apples to oranges. IQ tests are standardized. This is an example. An IQ tests are standardized so that the mean equals 100 and the standard deviation is 15. So by doing this, IQ scores are comparable even when using different tests. All right, there are several different IQ tests. Why do we need them? To compare combined variables measured in different units. Let's say that we want to compare. Let's say that we want to compare the income in dollars and number of years of education in years, or the number of cigarettes smoked per day and life expectancy in years. When all the scores in a distribution are converted to z-scores, the distribution of these new scores is referred to as a z-score distribution. The three key characteristics of the z-score, Raviter and Wallnow tell us, are the shape of the z-score distribution will be the same as the original distribution of raw scores. So the curve is not changing shape. The z-score distribution will always have a mean of 0. Whoa, isn't that cool? So when we grab and convert to z-scores, what's in the middle? What's the mean? 0. 0 is always going to be the mean. Third, the z-score distribution will always have a standard deviation of 1. Well, isn't that easy to work with? And that's why we do these little beggars. The z-score distribution is always going to have a mean of 0, and it's always going to have a standard distribution of 1. Here's right from the book. A population of scores is transformed into z-scores. All right, as you can see, the transformation doesn't change the shape. The shape in both of them remains exactly the same. All right, the one on the right here is the z-scores. So these are showing the x values. So in here, the mean is 100 and the standard deviation is 10. All right, you could tell that because it's 110. Just like I said, the only change is that the mean of the distribution is now 0, and the standard deviation is equal to 1, both on the plus side and the negative side. Wow! So when the z-score transformation, with the z-score transformation, the x-axis or raw scores is relabeled into z-score units. So we take it It's no longer the x, it's now z-score units. Got it? Distance of one standard deviation on the x-axis equals standard deviation equals 10 points in the above figure equals 1 point on the z-scale score. So, the z-score distribution is a universal yardstick to evaluate the position of an observation in relation to the distribution. Pretty neat, really, when you think about it. The z-transformation doesn't alter the shape of the distribution. If the original distribution is positively or negatively skewed, so is the z-score distribution going to be. The z-distribution will only be a normal distribution if the original distribution is normal. All right? You remember, normal distributions are a family of distributions that have the same general shape. They are symmetric. And what do I mean by symmetric? That means that they aren't positively or negatively skewed. All right, they're symmetric, so they have kind of even, whether they're leptokurtic like this guy or platykurtic like this guy and this guy, they're going to be equal on both sides. They're going to be normal distributions. They're going to be equal on both sides. Okay, they only differ in how spread out they are. The height and width of a normal distribution depends on two parameters, and here they are: the mean and the standard deviation. Here are some other characteristics of the standard deviation. The observation with the highest frequency falls in the center. And I'm sorry about this, but I had the Canadian spell checker on, and it did that to me. With equal curves on both sides of the center. Half of the values fall below the mean, and the other half fall above the mean. Symmetry implies that the mean equals the median equals the mode. Okay, remember what we talked about and how to figure out mean, median, and mode. So if we are in a positively skewed distribution, it's going to be mean, median, and mode. If we're in a negatively skewed distribution, it's going to be mean, median, and mode. Okay, but in a normal distribution, what's it going to be? It's going to be mean, median, and mode. Symmetry also implies that the frequency of values above the mean will be equivalent to the frequency of values below the mean, on the condition that the distances between the values and mean are the same. They're identical. Values with the lowest frequency are those that are the farthest away from the mean on either side. Okay, so you remember, I mean, as you get more and more away from the mean, you're going to have them distributed farther out under the tails of the curve. Why are normal distributions important? Why do you think? Because they're the most widely used distribution that we use to describe continuous variables, interval or ratio variables, numbers. It's said to have a well-behaved distribution. It's easy to, it's said that it is a well-behaved distribution. It's easy to manipulate. Conditions for the use of many statistical tests lie in the fact that they are normal distributions. It's used to find significance levels in many hypothesis tests and confidence intervals. We'll be talking about those later in the semester. And sampling errors are often normally distributed, especially as sample size increases. That's called the central limit theorem, and we'll talk about that also a little later. The standard normal distribution is a big concept. There are many normal distributions. They all have the same underlying pattern. All right. For purposes of comparison, it's useful to transform all the normal distributions into one standard distribution that serves as a reference point, the standard normal distribution. All right. This is important. The standard normal distribution. The standard normal distribution. If the initial distribution is normal, the z-transformation creates a standard normal distribution. So you kind of already know how to do that. All right, here it is. The standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. Hey, where'd you hear that 4 slides back? How to assess the normality of a distribution? Well, you could do it graphically. You could do a histogram. The limitation is that it's not very precise. It's just approximate. You could use the Kolmogorov-Smirnov test, and the Smirnov is not the vodka. It's a statistical test. But the limitation on that is that it doesn't indicate the degree of deviation. Even minor deviations are identified, especially in larger samples. We could use the Shapiro-Wilk test, and that's the same as the Kolmogorov-Smirnov test, but it's recommended when the sample size is small. And these are all things that are in SPSS, so don't get the shakes. Quick trick. If the kurtosis divided by the standard error of kurtosis and skewness divided by the standard error of skewness are valued between a -2 and 2, then the distribution follows a normal distribution. And if you remembered, those numbers come up when we do a computation in SPSS. In other words, the value of skewness and kurtosis should not be more than twice as high as the value of their standard error. This method is sensitive to sample size. Okay, let's take a look again at skewness. And we're coming up on about 11 and a half minutes here, so I'm going to try to pack this in. The skewness over here is a negatively skewed distribution. Here is a positively skewed distribution, and this distribution is not skewed rather, sorry. Kurtosis. This is a platykurtic distribution, a leptokurtic distribution, and a mesokurtic distribution. Meso means the middle. How do you normalize a non-normal distribution? Well, in SPSS, we could use a log transformation, or we could recode extreme values, generally values that are beyond plus or minus 3 standard deviations from the mean. Some people choose to just leave out the extreme values, and I'll show you how to do a log transform in SPSS, and I'll show you how to recode the extreme values. Reminder about the empirical rule. If the distribution of scores approximate a normal distribution, the following holds true. You remember 68% of the scores is expected to fall within 1 standard deviation, 95% of the scores is expected to fall within about 2 standard deviations, and 99% of the scores is going to fall within about 3 standard deviations. The standard normal distribution, looking ahead to hypothesis testing. Okay, right now we're doing descriptive statistics, but we're going to move into something called inferential statistics. We're going to infer things from our numbers. All right, and inferential statistics use information about the location of a value on the standard normal distribution, that we got from our z-scores, for the concept of statistical significance. And we want our statistics to be significant because we want to make sure that we don't have a lot of error. Okay? Statistical significance, we'll talk about that more next week, is how likely it is that an observed score can be found in a population. Don't forget, we're dealing with a sample, right? And how likely is it that a mean found in a sample comes from a population with a similar mean? Okay, talk more about that next week. Here's another example. Randy scored 75 on a statistics exam. The class mean is 60 and the standard deviation is 10. All right, we're going to compute the z-score and explain the result. There you go. So we're going to take z equals x minus the mean divided by the standard deviation, and we come up with 75 minus 60 divided by 10 equals 1.5. I'm going to just move over to a very short next presentation.